Hello, I would like to welcome you to Lecture 11 of ENG3N03. We'll continue our discussion of the operational amplifier. I will give you a number of circuits that we will use them very often in operational amplifier applications, like the inverting amplifier, non-inverting amplifier, voltage follower, and so on. And I will try to give you some analysis of these circuits, and we'll have a number of examples. This one is taken from chapter 12. I believe section 3 and 4. I explained in the previous lecture that an OpAmp by itself has a very high gain. An ideal OpAmp will have an infinite gain. A practical OpAmp will have a gain of, say, 10 to the power 5, 10 to the power 6. The problem with this OpAmp is that you're not able really to amplify a signal in the way that you like. For example, if we have something like this one, if we ground the negative side, and this is the output, then if you have a signal here which is, say, 0.1 volts, if you connect something like this to an OpAmp, because of its high gain, this 0.1 volts will result in the output saturating, so reaching the maximum possible output voltage, which is going to be the VCC, or the positive supply voltage. So you are not able to amplify this signal, say, by a factor of 4 or factor of 5. So an OpAmp by itself is not really that useful amplification unless we introduce to it this concept of negative feedback. So negative feedback is when we return part of the signal in the output to the input, and then we return it here to the negative part. And as I will show you a number of examples, this guarantees that you can get precise amplification of your signal. You can get an amplifier that gives you a voltage gain of 5 or minus 5 or whatever voltage gain you desire, not infinity or very high as we get for an open circuit or with an OpAmp with no feedback. So I will be showing you a number of circuits that use this feedback. One thing I should mention, that if you have a positive feedback, this sometimes can be used to create oscillations. You can create an oscillator, so a circuit that creates sinusoidal oscillations or square wave oscillation, whatever the case may be, by adding some feedback to the positive side. Because when we add feedback to the negative side, we are subtracting from the output signal, while the opposite is happening when you feedback to the positive side. One of the most useful amplifier configurations we use is the non-inverting amplifier, and for this one we have two resistances. They are both connected to the negative input of the OpAmp, and then the input signal is applied to the positive terminal of the OpAmp. The analysis of this one is extremely simple and follows the same rules that we applied in our lecture. The positive V plus must be equal to the positive V minus. This means that the voltage at this point here, this is equal to Vn. Okay? Now, because there is no current flowing into the negative side, in the negative terminal, there is no current flowing here. All the current that flows in RF must flow in the other resistor Ri. So this means that we can write one equation saying that this current is equal to this current. This current here is equal to V out minus Vn over Rf, and this current is equal to Vn minus 0 over Rn. So if you put these together, you have, can simply write this one, this form, that V out minus V input over Rf will be equal to the other current, which is Vn minus 0 divided by Ri. Or if you move all terms, sum all the terms related to a Vn on one side, you should be able to show that V out over Vn, here you get two terms from the input, 1 over Rf and 1 over Rn, and the sum to one another, so 1 plus 1 Rf, 1 plus 1 Rn plus 1 over Rn, and then you multiply both sides by Rf, and then when you do that, you get that V out over Vn is equal to 1 plus Rf over Rn. This is called non-inverting amplifier because if you have a sine signal, a sinusoidal signal, the output will be in phase with the input. It will be also a sinusoidal signal, but with an amplified amplitude. So this one does not create any phase difference. It's a non-inverting amplifier. So this one, I would like you to memorize it. It's something we use very often analyzing OpAmp circuits. This configuration here, which is called non-inverting amplifier, its gain is 1 plus R, R2 over R1, or 1 plus RF over Rn, as shown here. Now for this amplifier, I would like to draw to your attention to one thing. The input resistance seen by the source is infinite, because looking into the positive input of the op-amp, there is no current flowing in. Then this source is really an open circuit, which is a desired feature in any amplifier. One other thing, the output resistance seen by this op-amp, if I connect it to another stage, the output resistance seen is also 0. And I will explain this to you in a later example, but the way we do it is that we replace this amplifier by its equivalent circuit. So the equivalent circuit will look something like this. This is the input resistance, Zn, and then you have a voltage source. This is AV, Vn, and this is R out. This is as the same way I explained it today I explained it in the lectures. In order to determine this R out, what you have to do, you have to remove this voltage source. And how we remove it? We remove the input. So if we make this one short circuit, if you remove the input, then the resistance seen from the output side is simply R out, because this source disappeared. Okay, if you make this one 0, then this one must be 0. Then the voltage here is 0. Then there is no current flowing in this branch. Then there is no current flowing in this branch. Then the voltage here is equal to 0. So this means that if you apply a current source at this side, and this is how we do it for a circuit like this one, we apply a current source, and this current source, we call it IXA here in this case. Then this current source will see a 0 voltage across it, because the current here will all sink into the op-amp. There is no current flowing in these two branches. There is no current flowing here, and the voltage here is 0. So it looks as if this current source is really flowing into a 0 resistance. So the equivalent output resistance seen from this side is 0. So this amplifier, if I want to replace it by this equivalent circuit, I will replace it by an infinite input resistance, 0 output resistance, and a voltage gain of equal to 1 plus Rf over Rn. And these two are very desired features, that the input resistance is infinite, the output resistance 0, as I explained in the lecture. This is what we expect from an ideal voltage amplifier. Another circuit that we use very often as a buffer is this circuit. When we take the limit, when we make Rf goes to 0 and Ri goes to infinity. So this becomes open circuit, this becomes short circuit. Then the gain of a non-inverting amplifier, which is 1 over Rf over Rn. You take the limit as Rf here, this one will go to 0, and this one goes to infinity. 0 over infinity will give you 0. Then the gain of this circuit, the gain that you will see in this circuit is simply equal to 1. Why would I create a circuit that creates, which is effectively this one here, why would create a circuit that will give me a unity gain? The reason is that if you have a weak source that's not able to give enough current, it's a very weak source. So what you do, you connect it to a circuit like this one. The output will follow the input, but the current that will be supplied to the address of the circuit is really coming from the powerful op-amp. The op-amp is really able to supply stronger current. This is why when we have a weak source that's not able to supply enough current, we connect it to a buffer. And then this buffer, we can use it to supply any number of outputs, and the output here will follow the input here. It's called a voltage follower. Very interesting circuit. And here the input resistance seen by this voltage follower is simply equal to infinity as well. One other circuit we see very often as well, and I explained this one of the examples earlier, so I'm not going to go into the theory of this one. It's called the inverting amplifier. V output is simply equal to minus Rf or R over Ri multiplied by Vn. So that if the input is a sinusoidal signal, the output is an amplified sinusoidal signal, but with a phase shift of 180 degrees. So if this is your input, okay, then the output will look something like this one here. It will be a phase shift 180 degrees but it's an amplified version of the input. And this amplification ratio is really determined by the ratio of RF to RN. And for this one, and I will show you in one of the examples later, because this is ground here, this is ground, the input resistance Rn, okay? So the input resistance is not infinity as we would desire, but the output resistance of this one is 0. And the reason for that is that if you short the input, and then if you connect a current source at the output here, this current source here, we call it Ix. This is the way we determine the output resistance. Short the input, remove the input, and then connect a current source, and then to try to determine the voltage drop across this current source. And this voltage drop will tell you what is the resistance seen from the output of this amplifier. Now, if I make this one short circuit, then this one here, the voltage here is 0. The voltage here is also 0. Then there is no current flowing here. The current flowing here is equal to 0. But this current must be equal to this current, because this whole current will flow this way. Nothing flows into the OpAmp. So if the current here is 0, then the current here must be 0 as well. Then if this point is 0, then this point must have a voltage of 0 as well. So regardless of Ix, the voltage is equal to 0. This is simply saying that the output resistance of this inverting amplifier is equal to 0. One other thing to remember about an OpAmp is that the OpAmp itself really supplies a very high gain over a certain bandwidth, but gradually and slowly this gain starts to decay, and it goes from 10 to the power 6 up to only a gain of 1, say beyond 1 megahertz. So just remember that an OpAmp will act as an ideal amplifier only within a certain bandwidth, but its very high gain starts to decay gradually and slowly as the frequency of the input signal is increasing, until we reach a certain frequency. It's called the unity gain frequency, where it gives you only a gain of 0 dB or a gain of 1, unity gain of 1, ratio of 1. So this one to keep in mind. I'm not going to be asking you to know more about this, but just to remember that the OpAmp supplies its intended high gain only over a limited bandwidth. But beyond that, the gain will start to go down gradually and slowly at minus 20 dB per decade. So every time you multiply the frequency by 10, the gain will go down by 20 dBs. Okay, let's consider a number of examples. This one here is an inverting amplifier. Immediately when I see something like this, I know that the gain is minus R2 over R1. I don't have to think about it. I don't need to prove it, okay? For this circuit, we are required to determine the gain, determine the current being drawn from the source, determine the current being drawn from the OpAmp I out, and determine the value V out. And we are given a number of parameters that R2 is equal to 68K, R2 is equal to 360 kilo ohm, R1 is 68K, and the input voltage is very small, it's 0.5 volts. So we know the gain is automatically equal to minus R2 over R1, so it's minus 360 divided by 68. We don't have to drive that. What is the current drawn from the source? We agreed, because this is ground, this will be virtual ground as well. Then the current is equal to Vs minus 0 over R1, and then I can get Is. Vs is 0.5 volts, R1 is equal to 68 kilo ohm, then we know what's Is. Now, what is I naught? Here we are not assuming that there is any other circuit connected to the output. So whatever currents flowing from the OpAmp will have simply to go this way. So we can simply draw this here. Whatever current is flowing from here will have to flow this way. And because there is no current flowing into the negative terminal, this current will have to continue into R1. So this is simply saying that the current I naught plus the current Is must be equal to 0, because these two are two currents flowing into that node, or that I naught is minus Is. Now what is V out? V out is simply equal to the voltage gain, which is minus R2 over R1 multiplied by Vs. So you simply multiply the 0.5 by the gain obtained from this ratio here. Okay, so as I explained in the previous slide, I don't have to derive the gain. The gain is simply equal to minus R2 over R1 minus 360K over 68K. I cancel the K with the K here. Doesn't matter, it's a ratio. This will give you minus 5.29 as a ratio of gain. Of course, you can convert this one to dB if you want. You have to remove the negative sign before that. V out is simply equal to AVVN. It is a DC circuit. If you apply a 0.5 volts, this circuit will amplify by minus 5.29. You multiply minus 5.29 by 0.5. You end up by minus 2.645 volts. We agreed that IS, the current drawn from the source, is equal to Vs minus 0 over R1. So it's 0.5 minus 0 over 68K, and this will give you 7.35 microampere. We agreed as well that I naught is equal to minus Is because there is no load, there is no load resistance, and there is no current flowing into the negative terminal. So I naught is equal to the negative of this value is equal to minus 7.35 microampere. Okay, for the short circuit, we would like to determine the voltage gain, the input resistance, and the output resistance. The voltage is again an inverting amplifier, but I'm showing this one because I want to stress that any voltage amplifier can be replaced by an equivalent circuit. This circuit represents the input resistance, a voltage controlled voltage source, and then an output resistance. And I would like to replace this whole circuit by its equivalent representation of the voltage amplifier. I know that the gain is very simple. The gain of an inverting amplifier is minus R2 over R1, so it's minus 5 over 1 is equal to minus 5. I know as well that the input resistance is the resistance seen from this source, because this ground is going to be virtual ground, so the resistance seen between this point and the ground is simply 1K. In order to determine the output resistance, we have to short the input, we have to remove it, apply a current source at the output, and then determine the voltage drop across this current source. Okay, as I explained to you earlier, any voltage amplifier can be represented by this equivalent circuit. This is the input resistance seen from my source, the one I'm amplifying. This is the voltage controlled voltage source that gives you the voltage gain, and then there is an output resistance. Ideally, for an ideal amplifier, we would like to have an input resistance of infinity and output resistance of 0. But for this circuit, we know that the input resistance is really limited, okay? Is low. But the output resistance, as I will show you, is really nothing but 0. How I determine the output resistance? I simply have to remove that source. I remove that source by shorting Vn. If you make this equal to 0, then this voltage source is equal to 0. Then the resistance seen between these two terminals here and here is R out. And I can simply apply a current source between these two terminals, and then the voltage across it will determine for me what's R out. Now, the gain here for this circuit, this is an inverting amplifier, is equal to minus 5K over 1K is equal to minus 5. This is known. The input resistance as we agreed is simply equal to the 1K ohm. This is the resistance seen to the virtual ground. Now we'll move to determine the output resistance. So for the input resistance, as we agreed, this is ground, this virtual ground. Then the resistance seen between here to ground is simply equal to 1K. And the input current is equal to whatever voltage you put here divided by 1K. So Rn is equal to 1K. Now we move to determine the output resistance. For the output resistance part, this is what I'm going to be doing. I will remove the input in order to remove the voltage controlled voltage source, and then I will apply a current source at the output. And then the voltage across this current source will be equal to this current, which is simply a test current, can be 1 ampere multiplied by the output resistance. Now, because I remove the input source here, this is ground, and this is ground. Then there is no current flowing this way. I1 must be equal to 0. But because there is no I minus, there is no current flowing into the OpAmp, I2 must be equal to I1. If I1 is 0, then I2 must be equal to 0. So if the voltage here is 0 volts, then the voltage here must be equal as well to 0 volts, regardless of this current source. So this means that the resistance seen by this current source is equal to 0 ohm. Or the output resistance, this op-amp is 0 ohm, which is a desired characteristic. But this one does not have an infinite input resistance. It has a 1K input resistance. So this whole inverting amplifier can be represented by this equivalent circuit: a 1K input resistance, a voltage controlled voltage source of a gain of -5, and a 0 output resistance. So when we cascade a number of these amplifiers together, we can cascade them through this equivalent circuit here. Okay, we have here, this is one of these non-inverting amplifiers. We discussed that earlier, but I added this extra resistance here. I would like to determine what is the gain of this voltage gain in dB. I would like to determine what is the output resistance. And I would like to take, if Vn is equal to 0.25 volts, I would like to determine what is V out, what is the output voltage, and what is the current drawn from the op-amp. Okay, this is a non-inverting amplifier. We have derived that earlier. Actually, this resistance does not really add much to our calculations, because Vn at the plus terminal is equal to the negative terminal, and the same analysis applies. This one here only changes the input resistance seen from the source side. So the gain is simply equal 1 plus 39 divided by 1. So the gain is equal to 40 as a ratio. If you want to convert it to dB, you get the log of 40 and then you multiply by 20. Now, what is the input resistance seen? The input resistance is simply equal to this 100K in parallel with infinity, because the resistance seen looking into the op-amp is infinity. So the input resistance seen in this case is not really infinity, is equal to 100K. Why would I put a 100K like this one? Maybe there is a capacitor in the previous stage that needs to discharge. So this is why I allow this, this 100K would allow such a capacitor discharge. So this may be one possibility for having something like this. Now, if Vn is equal to 0.25 volts, what is the output? The output is simply equal to the gain, which is 40 multiplied by 0.25. So this will give you the value of 10 volts. Now, how do I determine I out? Very simple. This current I out, because there is no load connected, will have to flow into the into this resistance here. So if I have here, say, a 10 volts at the output, then because there is no current flowing this way, then V out will be equal to this 10 volts divided by 40K, 39 plus 1K. And remember, because there is no current flowing here, the complete current will flow I naught will simply flow this way. Okay, this is a summary of the steps already explained. The gain for non-inverting amplifier, even with this extra 100K, is 1 plus R2 over R1. So 1 plus 39K over 1K will give you 40. You want to convert this one to dB, is very simple. It's 20 log to base 10 of 40. If you multiply this one, this will give you 1.6. You multiply by 20, you get 32 dB. Now the input resistance, as I explained, for this modified amplifier, it is equal to 32 kilo ohm in parallel with infinity. I'm not drawing it correctly. This in parallel with infinity. Okay, why is infinity? Because looking into the terminal of the op-amp, I see infinity. And when you have something in parallel with infinity, you get 100K. Now, if you have a 0.25 volts at the input and the gain is 40, then the output will be equal to the voltage gain multiplied by 0.25 is equal to 10 volts. And as I explained to you earlier, the output current, which is flowing out from the op-amp, will flow into the 30K and the 1K resistor. Then this I output is equal to V output divided by 40K, was equal to 10 volts divided by 40K, is equal to 0.25 milliampere. So this solves all the parameters of this circuit here.